We are talking about exploiting hardware-backed keys. One of the features of our platform. So we are both working for IBM, and especially for bringing Linux and other open source software to the S390 platform, or how they call it in marketing, IBM Z, is a platform for big business. So it's mainly also known as mainframe. And there are a lot of cool features in this old thing, and we are trying to bring it to life and to the people. So yes, before we come to the interesting part here, the last two topics, we need to give you some introduction. First of all, I will show you or guide you through the idea of hardware-backed keys. What are hardware-backed keys? IBM Z is not the only platform that having these features. So we will see how other platforms are doing that as well, and then we will switch the presentation to Reinhard, and Reinhard give you a short introduction about the C-specific things, and then we are talking about how we plan to exploit these features, and all is based on the new API, which we already heard about, the EVP ASCII API, the talk from Dimitri at the first day of the conference. This is the basis for all that. Okay, so what are hardware-backed keys, or if we are talking about hardware-backed keys, what do we mean, or what's the background? So the idea of hardware-backed keys is that the key material, the clear key, is hidden from the application, is hidden from the operating system, is hidden or never shown up in main memory, that is readable by applications or operating systems. So it's some kind of being deep in the hardware, and it's accessible only for a set of operations working on that keys or key material. And different platforms are implementing that differently. So there are also, for example, embedded platforms which are handling that in some kind of attached coprocessors. And in our case, in IBM Z, we have some kind of wrapped keys. Details will follow, presented by Reinhard. And so this is, it depends. The feature depends on how the hardware implements it, and there is mainly involved some firmware or CPU feature or whatever, which is then providing access or operations to with that key material. In our case, it's cryptographic operations. So the clear key for the operation is hidden, but we can do operations on with this clear key. So even if someone compromises our system, the operating system, it's not possible to read out the key material. It's only possible to read out the rest of the memory, what is a bad thing, but the key cannot leak. So, and we are it's our opinion that this is worth to bring it to life, bring it to people, bring it to the applications. so that this feature can be used. Okay, so then I will hand over to Reinhard.
Hello from my side. Now I want to present you with a specific form of hardware-backed keys. These are, well, keys. No, did I go forward? Yeah. I went the wrong way.
Yeah.
Yes, so, and these hardware-backed keys are provided by a feature that is inside our CPU. That feature is called Central Processor Assist for Cryptographic Functions, or CPACF, or CPACF for short. And it includes an instruction set for, well, IBM is an American company, so mostly NIST certified crypto algorithms, mostly symmetric algorithms, but also hash algorithms, some easy algorithms, and HMAC is a very newest addition to these algorithms. That instruction set, well, IBM Z is a CISC machine, complex instruction set computer, as complex as it gets, because each instruction implements, for the symmetric keys, a complete mode of operation. Meaning it may be a CBC operation, it may be AES GCM operation, and that means you give the instruction a key, or some control block, among others containing a key, and a pointer to a message that may be a gigabyte in length. And the instruction just does it.
One instruction call.
Yes, a single instruction. Clearly, you cannot monopolize the CPU for the length of gigabyte computation, encryption or decryption computation, so the instruction must, of course, be interruptible and resumable in case there's some timer interrupt or whatever. So they are long running. Yes, I think that is the important part here. Now, these instructions work on two types of key objects. One key object is what we call clear key objects. A key is represented by its value in memory. So as with every other platform, but we have a second representation, and that is what we call protected keys. So protected key can be derived from different origins, and I get to that later on. It could be a secure key from one of the IBM Z HSMs. It could be a retrieval secret. I get to that later on. Or for development and test purposes, you can, of course, turn a clear key into a protected key. There is a function that allows you to derive the protected key from these origins. And these protected keys are, well, keys that are wrapped by a hidden wrapping key. That wrapping key is specific to the virtual server, so the virtualization concept of IBM Z includes this support that each virtual server has its own wrapping key, meaning that wrapping key is different for different virtual servers on the same machine. And if you restart your machine, well, the second instance of maybe the same guest, of maybe the same workload, will get a new wrapping key. So protected keys are volatile in nature, and whenever you start using them, you have to have your origin at hand to first derive the protected keys. But from then on, the protected key is not in memory. Although the plain text value of the protected key is not in memory, it's only in the wrapped form. The clear key will only be inside hidden memory that only trusted firmware has access to, and the wrapping key itself, of course, is not accessible to anything outside that hidden firmware. So that means no hardware operator gets to that, no hypervisor gets to that value, and clearly the operating system itself doesn't get to that value. And not even if you dump the whole system, these areas will not include the wrapping keys or the plain text part of that keys. Okay, I think. So let me just explain a little bit how these key origins work. Here is one example. These are the secure keys. Secure keys are the HSM protected keys that we have. Our HSMs are almost stateless. They have very little memory. The memory contains a master key. That master key is used to wrap other keys. So the key objects that we deal with are wrapped keys. So you can generate such a key object on our HSM. You get a secure key. You can then give the secure key to our HSM and ask for a protected key. And the HSM will negotiate with our firmware to turn the value inside the secure key into a protected key. By the way, the I/O path between our crypto adapters and the firmware is uses a post-quantum protocol, and the user space gets back the protected key wrapped by the firmware wrapping key, and then can use it with CPACF. Another option for deriving a key for an origin are so-called retrievable keys. Retrievable keys is a very new concept that we introduce with our confidential computing systems. So secure execution is IBM Z confidential computing implementation. It, among others, has a component that is called ultravisor. The ultravisor is the firmware part, the trusted firmware part of the trusted execution environment, and it may store keys on behalf of a secure guest. So I'm not going into the details how these keys get into the ultravisor. Get me on the gangway afterwards in the hallway and I explain everything. But the ultravisor may maintain those keys. The guest itself, the virtual machine, will never see it, but it may know the identifier of the key and may ask the ultravisor, please give me that key object. And the ultravisor says, yeah, surely I do so, and gives back not the key value itself, but the key as protected key wrapped by the wrapping key of that very virtual machine that is protected by confidential computing. And now, given that we have those keys, we want to use them, and we want to use them with the most common interface. And that's where Holger comes into play again.
Okay, so now we want to exploit these protected key feature. So before I came to the EVP key API, I would like to give you an overview how we did it in the past. So there was a platform-specific implementation of a small library. We called it libcpc. So if you're Googling about this term, you will find the GitHub repository we have. And this is maybe a very minimal implementation. So it looks a bit similar to the APIs we are familiar with from OpenSSL. It has contexts. You can initialize the context with key material. You can initialize the context with an IV and so on. But it deals only with this kind of protected keys. And it's, as I already mentioned, minimal implementation at clean code base. These are the features on the plus side, and on the downside, we introduced with that API a very platform-specific API, which is only usable on our platform, Linux and System C. So from a point of view of an application developer, it would need to cause platform-specific changes to the application. So, and This is a really hard part to just modify the application so that it is enabling such a feature only for one platform. And then you also have to choose, would I only want to go this way, or would I also want to have clear key support as well on the same platform? So this is the downside of our current concept. So we were looking for a solution for that some years ago, and Nicola already tried to get such a feature like the EVP-S key transparent or opaque key objects a few years ago, and now we are very happy that that happened, driven by Jakub, Dimitri, Simo, so that we are now can using it as well. So since OpenSSL 3.5, we have this EVP-S key API. It's an API, Dimitri already told that. It mainly has opaque key blobs, which are used to perform operations for symmetric cryptography. It's somehow similar to the EVP-P-key API. There as well, we have opaque key blobs, so the key can be whatever the provider defines, and it can has attributes, different key formats, raw key formats, and so on. And so we have with the EVP-S key API the same now for symmetric operations, and that's a very good thing. So in the future, we want to move our libCPC more towards a CPC provider, so that on our platform, this provider can be installed, configured, and used by choosing the right key material. And yeah, then the application don't need to have any changes, and the application can then use the hardware-backed keys. So on the plus side, we will have a common crypto API for applications, so the application don't need to be modified, especially for our platform. So it's just running on every platform, on every Linux platform using OpenSSL, and it can be compiled for x86, for ARM, for RISC-V, and also for S390X, and can run on all platforms with clear key, normal clear key, and especially on our platform also using the feature with the hardware-backed keys. So this can be done and chosen by the configuration or the usage of the right key material. So yeah, on the downside, I've not found yet any problem that could hinder us from doing so. So Reinhard already mentioned the concept of the key origin and the protected key. So the protected key is volatile or can change between machines, because it is a wrapped key, and the wrapping key may differ or be different between machines. And so if you're moving a running workload from one machine to another machine, this could also mean that in the middle of an encryption, the protected key getting invalid. And we need to handle these kind of situations as well. So what we are store in an EVPS key object is only, or not only, but we mainly store the key origin. So the key origin is the part that is used if you are creating a key or importing a key. And this key origin will then be derived to a protected key by the S-key management or S-key manager, and it will also be rederived if an ongoing cipher operation is going will return with an error, and we will catch this error doing the rederivation and restart the encryption or decryption then after that derive. So, but this is so we will have the first derive here in the S-key manager, and then afterwards some other derivations in the cipher implementation. So this is a kind of special thing that we need to cover in our implementation. Okay, so EVPS key, Dimitri also covered this as well. So this is some kind of code sample without any error handling, how we expect that later an application could look like. We have an S-key import. We have a init for a cipher context. We have the cipher operations, cipher update and cipher final, and all that I think is already known to you, so it's nothing new. So, yeah, what we do in the S-key manager, I already showed this in the overview. We doing import and export of the key, so only the persistent key origin can be exported, so we never export any clear key material. We don't have it, so we cannot export it. And the protected key is also not part of the export because it's a volatile kind of data, so it doesn't make any sense to export that. Which kind of key origins would we like to handle? I think mainly the secure keys, which are sitting in or are wrapped with the master key in the HSM. We also want to support the retrievable secrets, which are used in confidential computing. And we also, for development and testing, especially known answer tests, it's good for being sure that all is working fine if you can do some known answer tests. Known answer tests also require some kind of known keys. So there is, I think, a good idea to enable or support also the clear key key origin, so that we can run those tests and make sure that that all is working correctly. Okay, I already mentioned export will be limited from limited use. I think we can export the key origin, but that's yeah, more or less useless for other providers, I think. So yeah, we should or we will try to figure out what's making sense on that side. Okay, and the main part of the S-key manager is then doing the initial derive of the key origin and creating the first protected key so that it can be used in the cipher. So the EVPS key object will cache this protected key, but it can be getting invalid over time. So, okay, and the symmetric ciphers, they are doing more or less the same as we do in the default provider with our clear key instructions. So, as Reinhard already mentioned, we have instructions doing full modes of operation, and we will in a similar way configure these instructions. So we will prepare the so-called parameter block. We will point to the protected key blob instead of a clear key key blob, and then just call the application, and the magic will happen. So hopefully the magic is the same magic as in ClearKey. And yeah, so the only differences between the ClearKey path and the protected key path is just the function code and the pointer to the key material, and also little path that is necessary for doing the rederivation of the protected key, so that if the protected key getting invalid, that we can renew it. So now let's come to the future. What we plan to do and what we are very, very highly interested in is to also have some decoder encoder support or store support. And Dimitri already mentioned that there is work in progress, so this will come up with the next release, I think. And yeah, what we are interested in, so I'm not aware of any other platform developer which is looking for bringing hardware-backed keys to OpenSSL for that specific hardware. So, for example, for an embedded platform, so there are from NXP these nice embedded boards which already have a component called CARM, which are able to provide similar functionality to the consumers. So, yeah, maybe we should keep in mind that if we are defining a file format for hardware-backed keys, we should think about not only us as IBM and System C, but also maybe other platforms which are interested. So if you know someone which is thinking in the same direction, please reroute it to me. I would like to get into a discussion and yeah, so that we can get some yeah.
Dimitri is raising.
Yeah. Okay, Dimitri?
May I give a comment?
Yeah.
As far as I know, PKCS 11 provider implemented support of private key as base as PEM wrapped URI. Jakob,
Yes.
correct me if yeah. So that looks something like that, and handling this URI in the provider backed store looks the most reasonable approach for specific formats.
Yeah, so the format that is used for the PKCS11 keys is just the URI. So unfortunately, for the hardware-backed keys, there is no RFC that specifies some kind of URI, unfortunately. So maybe we should do that first and describe or design a URI for hardware-backed keys. I don't know. So and then we can use.
It does not have to be RFC. RFC is something that is usable for more or less universal.
Yeah. Okay. So maybe we can discuss this afterwards. So I'm highly interested in any idea how to do that. So that would be perfect. Okay. So what we I already mentioned the file format, and we also so the protected key feature is not only for the symmetric keys; it's also available for EC private keys. So the file format in the best case should also cover that case as well. That would be nice. Okay, so having a way to decide based on the PEM file or DIR file which provider is chosen, that would help us and especially the applications a lot, because then you can just replace the key file, and in the ideal world no other changes necessary, and you can use the protected key feature out of the box. So that would be the best case. So maybe we come to that point somewhere in the future. Yeah, and there is another question.
Actually, I think you have answered your question yourself. The easiest way is to use an URI for your specific provider. So, and then you can handle symmetric, asymmetric keys over this. And with the first part of the URI, you also choose the provider, and it's absolutely transparent for the application.
Yeah. Maybe that's the solution, yeah. Thanks for that. Okay, so let me come to the conclusion of our talk. We love the SKey API, so we are very happy to have this. It's similar to the EVP PKey API, and gives the same flexibility in dealing with opaque keys. And it helps us for getting this feature to our customers, because the current way using the libcpc is somehow a bit complicated. Not being the API is not the complicated part, but bringing the other library, the other crypto library to the application is complicated. Okay, and for the consumers, the advantages are also very huge, because depending on the configuration or the key material, you can increase maybe not the performance, but the security level of your application. And so this is very visible with the PKCS11 provider, because now you can just move your key material to the HSM, and then setting up the PKCS11 provider and use the file format which contains the URI, and the application can use it out of the box. So we would like to do something similar with the protected keys and give the consumers, the customers, another way to increase the security level of their applications. And our main goal is that we don't need any platform-specific crypto API in the future, because it's hard to use and it will never happen to that people will use that. Okay, so now we are done and open for a question.
Okay, thank you for that. Does anyone, actually I'll quickly leap in because there's already been 2 questions about formats. Have you guys looked at PKCS 15, aka ISO 781615? Because that seems to do exactly what you need.
Okay, so I have to look at that. Yeah, so we looked at PKCS 1112 because PKCS 1112 also has this concept of secure containers, or how it's called. I don't remember the correct name, but there are some pros and cons. Yeah, but I will look at that PKCS 1115.
Yes.
It was designed for smart card and HSM data storage. So
yeah.
Okay. Anyway, any other questions?
So is your provider now an interface to the existing lib, or did you rewrite all the calls to your implementation?
So at the moment it's only on my disk. I have to mention that first. And yes, it's currently only a wrapper to the library at the moment. But I would like to get rid of the library API, because now I already told that we have a context in the library. So, and now I have a context in the provider, and the provider, or the ASCII context then points to the context of the library, and so this is double work, and I think it's worth to get rid of this duplicated stuff. Yeah, but the inline assemblies will stay forever, so there is no change.
And given that we are IBM Z and compatible is one of our main promises, it will take a while until an API vanishes.
Yeah. So I can imagine to keep the API in a separate version for a couple of years, but new features will definitely go only to the CPC provider. Any other question?
Okay, maybe one more question.
Hi, thanks for nice talk. I'm not fully confident in all the hypervisor, ultravisor stack, but I wonder about something like a downgrading attack from the protected key to clear text key. You mentioned that for the testing development, there might be some clear key path. Does the HSM at any time allows exposing the key, or not at all?
No.
So you can turn a clear key into a protected key, but not vice versa.
Oh, okay. No, I see. Thanks.
So for testing, you know it's key 1, 2, 3, and you want to see whether 1, 2, 3 encrypts my message in a special way, and do that with protected key hardware.
And the HSM is not involved in that transition between clear key and protected key. We have another instruction for that. So this, yeah.
But then, can I test the HSM that it does what it's supposed to do on the known keys or not? Then, as a user.
So normally the key that is created by the HSM never leaves the HSM
There was
other than in wrapped form. So either as secure key to the consumer, or via an encrypted channel to the firmware directly.
But you can, of course, test whether working with a protected key has the same effect as working with a secure key on the HSM. That you can test.
Okay.
Hopefully, same result.
Thanks.
Okay.
Okay, thank you for that. If we
You're
can
done.